So today I want to talk to you about phase diagrams. Phase diagrams are diagrams that tell you the phases of a particular substance. So here we have a phase diagram. In this phase diagram, the y-axis, you have the pressure that is measured in the SI unit ATM, and you have temperature, and it is measured in the SI unit degrees Celsius. Notice that on this phase diagram that there are three distinct areas. Now this phase diagram is not drawn to scale, nor is this phase diagram based on any particular substance. I just drew the phase diagram free-handed just to explain to you how to read one. So this phase diagram has three distinct areas. The first area that you see is, I'm going to move this further up, and the first area that you see on the phase diagram is the solid area. Now the solid is right next to the y-axis, and then between the two lines you have liquid, and then right below the curve you have gas. There are 2 points that you need to know for the phase diagram. The first point is called the triple point, and this point right here in the middle where the 3 lines meet is the point on the phase diagram where the substance is a solid, liquid, and gas all at the same time. The other point that you need to know about is critical point. Now understand this, that there are many different critical points on a phase diagram, but the critical point that I am pointing out to you, that I am indicating right here, is between a liquid and the gas phase. Well, this critical point is at a certain temperature and pressure, and this point is the boundary, last boundary where a substance is separated into a liquid and a gas. After a substance, if you increase the temperature and the pressure of the substance, then that area right above the critical point is called the supercritical fluid. This area is known as a supercritical fluid, where the substance now at any place in this area right above the critical point, this substance happens to be both a liquid and a gas. So it has properties of both, and also it has the same density. So the substance is indistinguishable between a liquid and gas. So let's say that you have this substance that is 120 degrees, that is over and about 40 atmosphere. With this phase diagram, this substance at 40 atmospheres and 120 degrees Celsius would be a supercritical fluid, where it's indistinguishable between the liquid and gas phase. Another thing that you can look at in a phase diagram are the different phases that the substance is going through. The substance, when it goes from a solid to a liquid state, this we say that it is going through the melting phase. And what is happening? Melting phase, an example of that would be ice that is melting into water. And what's happening is that you have the solid that is clumped up, compact, rigid, where the molecules are not moving at all or hardly moving, to liquid, where the molecules are now further spread out and they're beginning to move faster. So the kinetic energy in the liquid is a lot higher. When a substance goes through the melting, obviously the kinetic energy increases, which means the substance is gaining energy into the system. So we say that the heat flow in this case is positive, and the energy reaction for the melting phase would be endothermic. On the other hand, if the substance happens to go from a liquid to a solid phase, where the substance is when the substance is spread apart and it is moving faster, and the molecules go to more of a solid phase where they're compact and rigid and not moving as much, we say that that phase change is freezing. So the substance is going through freezing. That means the liquid, an example of that would be liquid water becoming ice. In this case, the energy is now decreasing from the system. So we would say that the heat flow is a negative where it is leaving the system. So the energy reaction would be exothermic. When a substance is going from a liquid to gas state, we call that vaporization. An example of that would be steam. And then when the substance goes from gas to a liquid phase, we call that condensation. So an example of condensation would be the beads of water that you see collecting outside of an ice cold drink. So during the summertime. So what's happening is that you have water vapors outside the glass that are moving very fast, full of kinetic energy, and it is hot, so the temperature is very high at that time. But as those water vapor molecules come in contact with the cold drink, the temperature of those water vapor molecules drops, and because the temperature drops, the molecules then become liquid molecules that collect on the side of the glass as beads of water collecting. Another phase that you have is going from a solid to gas. An example of that would be dry ice, and we call this phase sublimation. So what you have is the substance is going from dry ice is usually kept in a cold freezer, and as you take the dry ice, it's to room temperature, the temperature increases. So the dry ice, which is a solid, now becomes more vapor molecules. So that is called sublimation. The phase from going from gas to a solid, we would call that deposition. An example of deposition would be when you have frost that you see during the colder months of the year. So you have water vapor molecules in the atmosphere, but as the temperature drops during the nighttime, those same water vapor molecules now collect as ice on the blades of grass that you see, or we call that frost. So that would be an example of deposition. So you've got melting, freezing, you've got vaporization, condensation, sublimation, and deposition that is present. So I have here an example where where I have two phase diagrams, and let's see. Okay, so I have two phase diagrams here. I have the phase diagram for water and for carbon dioxide. You can see the different phases that both of these substances go through, but clearly by just looking at this, you can tell that these are two different graphs. That the water and carbon dioxide, each phase diagram is unique to the identity of the substance. So in this case, you can tell that for water, that the liquid happens to be a larger area, but for carbon dioxide, it is more of the solid, and the gas that happen to be larger areas where a very small portion of it is liquid. Another characteristic is that the triple point for water molecule is much lower than the triple point in carbon dioxide. in carbon dioxide, where the triple point is a lot higher. It is at a higher atmospheric temperature, as well at a higher atmospheric pressure, as well as at a very low temperature. Where over here you can notice that for water, you can tell that this substance is water because at 0 degrees Celsius, at 1 atm, the substance happens to be a solid, and at 100 degrees Celsius, this substance at the same atm happens to be liquid water that is now moving on to the steam right here. So you can see that at the same atm, 1 atm, the substance is a solid, and at 1 atm, the substance is also becoming a gas, or going from liquid to gas. So, and that is not the case for carbon dioxide here, where you can see at 0 degrees Celsius, that's not the case for this substance, nor is the boiling point, and the boiling point is very different on a carbon dioxide phase diagram. Another thing that you can see is the supercritical point, where the supercritical point in for phase diagram for water is at a very high temperature, but the supercritical fluid area for carbon dioxide is at a very low temperature. So this area for supercritical fluid happens to be a much smaller area, but for carbon dioxide it happens to be a much greater area. So this is just some simple characteristics of a phase diagram. So let's put this to practice now and answer some questions for a phase diagram. So you're given a simple phase diagram that basically looks like this, and you should be able to identify the three phases. So this would be your solid, your liquid, and your gas right here. You should be able to identify the critical point, which is right here, and you should be able to identify the supercritical fluid. The supercritical fluids will be formed in this area right here. Your triple point for the substance happens to be right here in the middle. So remember that all the phase diagrams that I'm showing you today are not drawn to scale. So if you're looking at this, the first question that we have is, what state of matter is this substance at 2 atm pressure and 31 degrees Celsius? So if we're looking at this 2 atm for pressure and 31 degrees Celsius, that would be right here at this spot. So it says, what state of matter is this substance? So we would say at 2 atm, 31 degrees Celsius, the substance happens to be gas. So you would put gas there. What happens to this substance if the temperature is increased from negative 78 degrees Celsius to 0 degrees Celsius at a constant pressure of 72 atms? So if you have about negative 78 to negative 78 at 73 atms would be right here, and you're going to 0 degrees Celsius to 73 atms. 0 degrees Celsius to 73 atms would be right here. So you're going somewhere from a solid to the liquid state. But the question is, what happens to the substance? Well, the substance is then going through the melting phase. Number 3, at what temperature and pressure is the triple point for this substance? So if we're looking at this, the triple point is right here in the middle. That means that at 5.1 atm, the substance is at triple point with a temperature of negative 56.7 degrees Celsius. So you would put 5.1 atms and negative 56.7 degrees Celsius. And then the last but not least is, at which pressure does this substance sublimate at negative 78.5 degrees Celsius? Well, in order to sublimate, the substance has to go from a solid to a liquid state. So at negative 78.5, that would be right on the graph at 1 atm. At 1 atm pressure, the substance goes from a solid to a gas state. So this was an explanation on how a phase diagram looks and how to read a phase diagram.